Hey everyone, and welcome to today's Explainer. Today we're going on a seriously fascinating journey through the evolution of digital video. We're going to explore exactly how humanity tackled the absolute massive technical challenges of capturing, compressing, and sharing our reality across the entire globe. From those very first clunky rolling film strips all the way to the totally immersive navigable holograms of tomorrow. Because really, the story of video is the story of how we connect with one another. Let's dive in. So here's our roadmap for the day. First, from film to pixels. 2, how digital video works. 3, the mechanics of streaming. 4, video accessibility for all. And finally, 5, the volumetric video future.
All right, Section 1, From Film to Pixels, Humanity's Quest to Capture Motion.
If we trace the path on this timeline, it's pretty mind-blowing. We start way back in the 1800s with bulky mechanical film cameras. Then we jump to the 1950s when 2-inch magnetic tape finally made video editing and broadcasting practical. Next, the 1990s hit, and digital videotapes totally democratized recording. Suddenly, everyone had a camcorder. And today? Well, we've got literally 8K resolution cameras just sitting in our pockets, using wild computational photography and AI to shoot cinematic footage anywhere, anytime.
Now, the stark contrast between these two eras is incredible. Think about it. In the analog days, every time you made a copy of a videotape, you'd get something called generation loss. Basically, every copy was just a little bit worse than the last, like a photocopy of a photocopy. But shifting to digital, that completely eliminated the physical degradation. Digital gave us perfect, flawless reproduction, instant playback without waiting for harsh chemicals to process, and, best of all, it untethered our footage from physical tapes entirely, so we could finally send it over networks.
Moving right along to Section 2, how digital video works. The invisible science of pixels and frames. Okay, so at its very core, digital video is basically just math and data in disguise. Unlike the old analog video that relied on continuous signals, digital video actually breaks our reality down into discrete, perfectly quantifiable pieces of encoded data. It's an illusion of continuous motion. So the key takeaway here is that digital video is just sampling reality across time and space. A camera takes our chaotic, dynamic 3D world and squashes it onto a flat 2D plane. And we measure this trick in 2 ways. First, spatial resolution. That's how many pixels are crammed into a single frame. And second, temporal resolution, which is your frame rate. Now, because the human eye maxes out at perceiving smooth motion around 60 Hz, digital video just needs to flash discrete images at you fast enough to trick your brain into seeing a seamless, moving reality. Take a look at this. It brilliantly illustrates how engineers actually approach this stuff academically. They model video as a multi-dimensional signal. It looks super complex, but basically, engineers have to carefully calculate these sampling rates based entirely on the absolute maximum frequencies our human visual system can even detect. All right, Section 3, the mechanics of streaming, distributing massive data globally. This comparison right here shows exactly why streaming totally took over the internet. I mean, nobody wants to wait, right? Streaming heavily prioritizes immediate consumption over hoarding massive gigabyte-heavy files on your hard drive. So instead of requiring you to download the whole file before hitting play, streaming continuously feeds you data as you watch. It saves your device's storage and gives you that sweet instant gratification. But to make that instant gratification a reality, we rely on a crazy complex, lightning-fast architecture. Think of this 6-step delivery pipeline like a massive global network of hyper-efficient postal workers. First, codecs like H.264 compress the raw video. Then they chop it up into tiny chunks, transmit those packets over the internet, buffer them on your phone or TV to smooth out any connection hiccups, decode the data, and finally play it back. And the wildest part? All of this happens in literal milliseconds. Now, to guarantee this pipeline is absolutely flawless, engineers use testing tools like these burned-in timecodes. By photographing multiple screens at the exact same time, they can track down to the millisecond how long a specific frame takes to be encoded, transmitted, and decoded. This kind of precision ensures that whether you're watching a live Super Bowl broadcast or just dialing into a really important work call, what you're seeing arrives in real time, zero buffering allowed. Which brings us to Section 4, video accessibility for all. Designing experiences for every viewer. Because, let's be real, a flawless, high-speed stream means absolutely nothing if the content itself isn't built for everyone to experience.
Let's start with captions, which are a total game changer for deaf and hard of hearing viewers. Now, closed captions are incredibly flexible, you can toggle them on and off, and they make the video super searchable online. But open captions? They act as a brilliant failsafe. Because they're permanently burned directly into the video feed itself, they guarantee your audience gets the full context, even if they're scrolling on a social media app that has a terrible, inaccessible video player.
For blind and low vision viewers, audio description is absolutely vital, and getting it right relies on strict precision. A narrator has to objectively describe essential visual elements, like unspoken actions or text on the screen, and they have to perfectly squeeze it into the natural pauses so they don't talk over the original dialogue. It basically ensures a viewer receives every drop of crucial visual context they need to fully experience the story just by listening. But here's the kicker. All of these beautifully crafted captions and descriptions are entirely useless if the video player itself is a roadblock. A truly accessible player absolutely must allow keyboard-only navigation for people with limited mobility. And it has to avoid auto-playing video with sound, because that will completely drown out a blind viewer's screen reading software the second the page loads. The tech delivering the video simply has to be as inclusive as the video itself.
All right, on to our final section. Section 5, the volumetric video future. Stepping inside the digital frame.
Enter volumetric video. Just imagine, for a second, hitting pause on a live basketball game, walking off your couch, and literally stepping onto the digital court to look right over the point guard's shoulder. Captured by dozens of perfectly synchronized cameras, heavy-duty algorithms actually rebuild the physical space, creating a 4D video that lets you, the viewer, control your own perspective in real time. It is straight out of sci-fi.
But there was a huge roadblock: data. A single 30-minute volumetric clip can easily balloon to terabytes in size, making it literally impossible to stream. But this is where it gets amazing. Researchers at Brown University created a method called PAC-UV. They ingeniously figured out how to take millions of 3D data points, called Gaussians, and map them down onto manageable 2D flat maps. It's kind of like unwrapping a globe and laying it out flat on paper. This breakthrough means we can stream entire 3D environments over the exact same internet architecture we already use for YouTube and Netflix today.
And they also solved another massive headache: tracking things in 3D space over time. In earlier 3D video, if someone simply walked behind a wall, the system would completely lose track of them and the whole illusion would break. But by intelligently chopping the 4D video into small chunks and constantly refreshing those tracking algorithms, the system can now reliably render super complex, half-hour-long scenes without ever losing track of the objects moving inside them. What this quote from Professor Sridhar brilliantly illustrates is that this isn't just a gimmick for movies and video games. Volumetric streaming is fundamentally about creating flawless digital twins of our physical reality. Think about it. From mapping out complex manufacturing floors to assisting in remote surgical operations, we're going to be able to instantly transport complete, fully navigable environments across the globe in milliseconds. So we've journeyed all the way from heavy, chemical-soaked film strips to fully navigable, streaming 3D holograms that run right on our existing internet. As the physical and digital worlds seamlessly merge together, the technology itself is no longer our barrier. The only limit left is deciding what reality you want to step into next. So what digital twin of the world would you explore first? Thanks so much for joining me on this explainer, and I'll catch you in the next one. Keep exploring.